Alright, hello everyone. It's been a long time. I hope all of you are doing really awesome. So today I'm going to be discussing the solutions to Codeforces educational round 131. This round just finished about an hour ago, and I'll be discussing the solutions to the first 4 problems from A to D. Talking about the round, I think it was a really nice and well balanced round. Problems A and B were nice and easy. C was also good, but it was kind of tricky for me, but overall a nice problem. And most of all, problem D was like really amazing. The best part about problem D was that the main idea required to solve it is very well known and trivial, but even so, it's not very trivial to think about. It's not very trivial to think that this is the idea that is going to be used in the problem, right? So yeah, that's going to be my take on the round. Nice and well balanced round. So without any further ado, let's start with the solution to problem A. Okay. So here we have a field of size 2 cross 2, and every cell is either a 0 or a 1. So every cell either contains a grass or it doesn't contain grass. What we can do in an operation is we can choose one row and one column, and we can cut all the grass in the entire row and the entire column. That means we can replace all the ones with zeros, right? And our task is to find the minimum number of moves required to cut the grass in all the non-empty cells of the field. So we have to make all values of Aij equal to 0. So there are 4 cells, and we have to make all 4 of them to be equal to 0, and we have to tell the minimum number of moves that we have to do. So the solution here is pretty straightforward, but still I would just demonstrate how we can solve this. Okay, so let's say this is a 2 cross 2 field that we have here. So here there are 2 rows and there are 2 columns, right? So what we can do in a move is we are basically choosing an entire row and an entire column, and there are basically just 4 choices. We can choose the first row first column, first row second column, second row first column, and second row second column. So in the first choice we will be clearing all 3 of these cells, right? And if we look at the second choice, if we choose the first row and the second column, we will be clearing these 3 cells. And if we choose the second row and the first column, we will basically be clearing these 3 cells. And if we choose the second row and the second column, so we are choosing the second row and second column, so we will be destroying everything here, right? So the main observation here is that in every move, we are choosing any 3 cells and making them all 0, right? And we can do this for any 3 pair of cells, right? There are 3 ways to choose 3 cells from 4 cells, and that comes out to be 4. And that means that in an operation we can choose any 3 cells that we like, and we can convert them to all zeros. So now it boils down to basic casework, and there are just 3 cases to consider. So if everything is good initially, so if all cells are 0, initially, then obviously answer is going to be 0, right? But if the number of cells which are 1 is less than or equal to 3, that means we can choose all of them together in one operation, right? So if number of ones is less than equal to 3, we can basically choose all of them in one operation, because we can choose any 3 in one operation. So the answer is going to be 1. Otherwise, basically if all of them are ones, what we can do is we can choose any 3 of them in the first move, and then we can choose the other in the second move. And so if all are 1, then answer is going to be 2. And these are the only 3 cases that we have to consider. And yeah, the problem is solved now. The code is pretty simple. We just calculate the sum of all the 4 numbers. If this sum is equal to 0, then the answer will be 0. And if the sum is 4, then the answer will be 2. Otherwise, the answer is going to be 1. Right? So yeah, this completes the solution to problem A. Pretty basic and simple. Now let's move on to the second problem. Again, a very simple problem. Not much to think about, but yeah, it can get tricky if you don't think about the right method. I'll give it that. So let's see. So basically in this problem, for a fixed, we have a permutation, and for a fixed positive integer d, we define the cost of a permutation p of length n as the number of indices I smaller than n, such that pi into d is equal to pi plus 1. In other words, pi plus 1 upon pi is equal to d, right? And the number of such indices is the cost of that permutation. So we are just provided in the input a number n, and what we have to do is we have to find the permutation of length n such that its cost is maximized, and we don't care about what the value of d is, right? So the d can be anything, the value of d can be anything, but whatever value of d we choose, we should make sure that out of all the d's and out of all the possible permutation, the cost of our chosen permutation is the maximum, right? So we have to find the permutation of length n and the value d with maximum possible cost over all the ways to choose the permutation as well as d. So choosing d is also our choice and choosing the permutation is also our choice, right? So yeah, this is the problem. So this was problem A. Now let's move on to the second problem. All right. So the main observation is that what we'll do is we will try to find the maximum possible cost of a permutation, and then we will try to achieve that cost. Because if we know what the maximum cost is and if we have successfully achieved that cost using a constructed permutation, then we know that our permutation is the required answer, right? So yeah, how do we find the maximal cost? So the maximum cost is basically what we'll do is, so for every number which can contribute to the cost, we will try to make it actually contribute. Now the question arises, which are the numbers which can actually contribute to the cost? So that is very simple to think about. So if for a number x the value 2x is less than or equal to n, then x can contribute to the answer. Why? Because if d is equal to 2, then we can have x and 2x side by side together, and then x is going to contribute, right? And we are choosing x and 2x because the value d is equals to 2 is the smallest value we can choose, because if we choose d is equal to 1, then there obviously can't be any index where p1 is equal to pi is equal to pi plus 1, since d is equal to 1 and we have a permutation. So if d is equals to 1, then the answer definitely is going to be 0. So the minimum possible value of d is 2. So what we'll do is, for every number x, if 2x is less than or equal to n, then x can contribute to the cost if d is equal to 2. Now our only job is to actually try and construct a permutation with d is equal to 2 such that every pair x and 2x are together. And the way to do that again is really simple. So what we'll do is we'll start with 1. So I'll just show you the construction. So the construction goes like this. We'll start with 1, then we'll go to 2, then we'll go to 4, then 8, so on. We will go to the max value that we can go to, such that, so now we are at a value y, and if 2y is greater than or is greater than n, then y is the maximum possible value that we can go to, right? Now what we do is, we have considered all these values, but the smallest value which we haven't considered is 3. So now we start with 3, and then we go to 6, then we go to 12, so on and so forth. And then we look at the next smallest value which we haven't considered, which in this case turns out to be 5. So we start with 5, then we go to 10, then we go to 20, so on and so forth. So this is the construction, and here I have made sure that for every number x and 2x are together if 2x is less than or equal to n. If 2x is greater than n, then obviously that number can't contribute, but if 2x is less than or equal to n, then I am making sure that it is contributing to my cost. So yeah, this is a valid construction. So for implementation, I'll just show you guys the code. The code is again not very difficult here. So what we're doing is we are maintaining a set of all the available elements which haven't been used yet. So initially no number is used, so I put every number in the set. And then what I'm doing is I'm finding out the smallest number which is available to me. In this case, we saw that 3 is the smallest number which is available. So initially 1 will be the smallest number, right? So we start with 1, and then what we do is we initialize a current variable as the smallest number which is unused, and then while current is less than or equal to n, what we do is we keep assigning the next number to our permutation as cur, and we keep doubling cur, right? And when cur becomes greater than n, that is when we break out, and then we go over this entire loop again and again, and that is how we get the required construction, right? So the main point is every time you choose the smallest number which is not yet chosen, and then you just keep doubling it, right? So yeah, so finally we just output 2 because d is equal to 2 is the chosen value, and then we output all the elements of our formed permutation, right? So yeah, this completes the solution to problem B as well. Now we'll move on to the third problem. This is a really tricky problem for me because the way I solved it during the contest was not a very optimal way, and I still don't know any proof of why my method works. But the solution which I'll be discussing is a much more simple and convenient solution to understand. So yeah, let's see. So there are n workers and m tasks, and the workers are numbered from 1 to n, and each task I has a value ai, which means that ai is the index of the worker who is proficient in this task. That means there is exactly one worker who is proficient in every task, and every task should have a worker assigned to it, obviously. And if a worker is proficient in the task, then they complete it in 1 hour, otherwise it takes them 2 hours, right? And the workers work in parallel independently of each other, and each worker can only work on one task at once. Yeah, pretty easy to understand. Every worker is performing his or her task parallelly along with other workers. It's not the case that at one particular time only one worker is completing his or her tasks, right? Okay, so basically we have to assign the workers to tasks in such a way that the tasks are completed as early as possible. So we need to complete all the tasks taking as less time as possible, and we need to output this minimum time in which we can complete all the tasks, right? So yeah, this is the problem. I hope the statement is clear enough. Let's start with the solution. Okay, so the solution here goes like this. The main idea is that so the main key observation to this problem is, that if we can finish all the tasks in x days, then we can also finish them in x plus 1 days, right? So we can so if we can finish the task in less than or equal to x days, then we can also finish them in less than or equal to x plus 1 days, right? Because x is less than or equal to x plus 1. So yeah, that's the main observation required to solve this problem. And as always, in every problem where you see such a property that if you can do this in x days, you can also do this in x plus 1 days, the first thing that you should think about, and that I should have thought about during the contest, is using binary search. So yeah, the main idea is binary search on answer. If you're not yet familiar with this technique of binary searching on answer, then you will find 1 or 2 lectures that I have done on this topic on my YouTube channel. So if you are not familiar with this, you should go check that out. I think I have done a pretty good job in explaining what this means. So yeah, so the thing we can do here is we can binary search on the answer. For the guys who know what binary search on answer is, I'll basically be assuming that you know what it is. So the only thing which we are required now is to write the checker function, right? So now we need a checker function. Now how do we write a checker function? So the first thing that we are going to do before we think about the checker function is that we calculate tot of I. So we calculate an array tot of I, where tot of I denotes the total number of tasks in which the worker I is proficient. So one worker can be proficient in many tasks, although for every task there is exactly one worker who is proficient in it. So first of all, we calculate this array. It is pretty trivial to calculate it. We can just do it. We can just calculate it in linear time. So now I'm assuming that we have this array calculated, and now let's try to find out a checker function. So let f of x denote whether we can complete all tasks in less than or equal to x days, right? So let f of x denote whether we can complete all the tasks in less than or equal to x days, and now we have to write a definition for f of x. So let's see how we can do this. So we have a function f of x, and what we'll do here is, we will try to find out the maximum number of tasks that can be completed in x days, and check if that value is greater than or equal to m, because at the end of the day we have to complete m tasks. So if the maximum number of tasks is greater than or equal to m, then we are done, right? So now what we'll do is we'll simply iterate on all the workers. So for I in workers, what we'll do is for the ith worker, we'll check tot of I, right? So there are basically two cases. So the first case is when tot of I, so when tot of I is greater than or equal to x. Now what happens in this case? Obviously one worker cannot take more than x days, because the total number of days is basically the maximum value of the number of days taken by every worker, right? So obviously no worker can take more than x days. So if tot of I is greater than or equal to x, that means there are more than x tasks in which the ith worker is proficient in. So we will just pick any x tasks randomly out of them and assign them to the ith worker, and he will take 1 day to complete each task. So in total he will take x days to complete these tasks, right? So the number of tasks basically, so we have a task variable. So these are the number of tasks which are completed. Initially it is 0. So what we'll do is we'll pick up x tasks in which the ith worker is proficient and give him to I. So tasks plus equal to x. This is what we're going to do. And the second case is, so case 2 is when tot of I is less than x. So there are less than x tasks in which the ith worker is proficient in. So it makes sense to assign all the tasks in which he is proficient to the ith worker, and out of the remaining x minus tot of I tasks, the tasks which he will be doing, he will not be proficient in. That means he will take 2 days to complete each tasks, right? So basically what we'll do is, first of all, we'll assign him all the x tasks. We'll assign him all the tot of I tasks in which he is proficient in. And now what we have is, we have x minus tot of I more more days remaining in which the ith worker can work, right? Because the only thing we need to make sure is that nobody works more than x days. So now we have x minus tot of I more days, but now every other task that this ith person is doing, he won't be proficient in. So he will take 2 days to complete each task. So the total maximum number of tasks that we can get is x minus tot of I by 2 plus tot of I, right? So yeah, this basically completes the solution. What we'll do is, finally, after iterating on all the workers, if tasks is greater than or equals to m, then return true, otherwise we return false, right? So I hope this is pretty easy to understand. So yeah, this basically completes the solution. We just have to do this binary search and this checker function can be used. So yeah, let's just have a look at the code. Just make sure I'm recording. Yeah. So the code is pretty simple. What we can do is we can initialize our L and R variables with L as 0 and R as a very high value. And then what we can do is, for each I, if tot of I is greater than equal to mid, which is L plus R by 2, we do tasks plus equal to mid. Otherwise we do task plus equal to tot of I plus mid minus tot of I by 2. Finally, if the number of tasks completed is greater than or equal to m, we do R is equal to mid. Otherwise we do L equals to mid. Here I am maintaining the invariant that we can always complete all the tasks in R days. So the final answer is going to be R, right? So yeah, this completes the solution to problem C. Now let's move on to the last problem which we'll be discussing, and I think this is a pretty amazing problem. Problem D. Okay, let's see what this is saying. So Monocarp had a permutation A of n integers from 1 to n, and then what happened is that he calculated an array of integers b of size n, where bi is equal to the floor of I divided by ai, right? So we have an array b. So now what happened is that we have lost our original permutation A, but we still have this array B, where bi is equal to floor of I by ai. And what we have to do is we have to print any permutation which corresponds to the particular array B. So we have to print values a1, a2 up till an, such that for all I by ai float is equal to bi. Okay. And they have also guaranteed us that the tests are constructed in such a way that at least one suitable permutation always exists. Okay. Cool. So this is the problem. I think the statement is pretty easy to understand. Now let's look at the solution. All right. So first let's analyze the condition which is given to us in the problem, and then we'll build the solution up from there. So basic observations. So one basic observation that we can do here is that what we are given is that bi, so bi is equal to floor of ai, floor of I divided by ai, right? Sorry. Yeah, so this is the condition which is provided to us, that bi is equal to floor of I upon ai. So what does that tell us? Well, let's say we have a condition like this, that x upon y float is equal to z. Then what do we infer from this? So we can basically have a range for x, right? Also we can have a range for y and we can have a range for z. So how do we have a range? Well, basically if floor of, so I'll just write floor here for clarity, if floor of x by y is given to be z, okay, let's just forget about this and just work with our initial variables. So we have floor of I upon ai is equal to bi. That means the actual value of I upon ai, so the actual value of I upon ai lies in the range from bi to bi plus 1, where bi plus 1 is not included, right? So the actual value of I upon ai is bi point something, and that something can be 0 or anything else, but it is strictly smaller than 1, right? So what that means is that the actual value of I upon ai is greater than or equal to bi. So this is the first thing. This is the first equation. And the second equation that we have is that the actual value of I upon ai is strictly smaller than bi plus 1. Right. So it is strictly smaller than bi plus 1. So what we can get from here is that, so now these are the two conditions that we have, right? So these two conditions can basically be translated as a range for I, right? So the first thing is that we can see here is that if floor of I upon ai is equal to bi, then so from the first equation what we can infer is that ai into bi, if we just translate ai to the other side, ai into bi is smaller than or equal to I, right? So now from here what we can do is we can translate bi to the other side and we can get ai is smaller than or equal to I upon bi. So this is again another very important equation that we have. So I upon bi. So let's just highlight it for now. So this is an important equation. Let's just write it down as 3. And now what we can get from this second equation is that, so in the second equation we have I upon ai is strictly smaller than bi plus 1, right? So now if we translate ai to the other side, what we'll get is I is strictly smaller than ai bi. I is strictly smaller than ai bi plus ai, or I is strictly smaller than ai into bi plus 1, right? And now if we do some manipulations here, what we'll get is we'll get another range for ai, and that range is that ai should be basically greater than or equal to I plus 1 divided by bi plus 1, and ceiling of it basically, right? So now we have this relation. So let's write it down as relation 4. So this is the fourth relation, that ai is greater than or equal to ceiling of I plus 1 divided by bi plus 1, right? Cool. And this is because if I is less than this value, then okay, I think I just skipped a step. So if we add plus 1 to the LHS, then we can remove this less than sign by less than equal to sign. So we get something like this: I plus 1 is less than ai into bi plus 1. So now from here we get that ai is greater than or equal to ceiling of I plus 1 upon bi plus 1. So basically from 3 and 4 we get a range for ai, right? So ai lies in this range. For every I, we get the relation that ai basically lies in I upon bi. Sorry, this is the maximum value. So the smallest value is ceiling of I plus 1 divided by bi plus 1, and the maximum value is I upon bi, right? Cool. So we have a range, right? The main thing is that we have a range. This mathematics is not very difficult. It took me some time to describe it here, but during the contest I think this can be done within 2 minutes. So yeah, the basic idea is that for each I we have two values, li and ri, denoting that AI should be greater than or equals to Li, and AI should be smaller than or equals to Ri. And there are no other restrictions that we have, right? If all these two conditions are satisfied for each I, then we will get the corresponding array B from our corresponding permutation A, right? So these are the only two conditions that we have to satisfy for each I. Cool. So with that in mind, now let's talk about the actual solution. So for the actual solution, what we'll do is we'll try to think about the position of the number 1. So we will try to find out the position of 1 in the answer. In the answer permutation that we will build, we will try to think about the position of the number 1. Now where can we place 1? Right, so obviously where we'll place 1 in an index I such that Li is less than or equal to 1, right? So L of I is less than or equal to 1 and R of I is greater than or equal to 1. This is pretty obvious, right? Cool. So if this is pretty obvious, what we get from here is that now if L of I is less than or equal to 1, that just means L of I is equal to 1 because 1 is the smallest value, right? So the main condition for placing 1 is that we can place 1 at an index I if and only if L of I is equal to 1. But now the question arises that a lot of indexes can have L of I is equal to 1, right? This value of ceiling of I plus 1 upon bi plus 1 can be 1 for many I, right? So how do we decide which index we have to assign the value 1? It turns out that we can just decide on the basis of R of I. How do we do that? So the claim is place 1 in the index where L of I is equal to 1 and R of I is minimum. So this is the claim, and this is the most important observation which is required to solve this problem, that we will place 1 only at an index where L of I is obviously equal to 1, but out of all such indexes we will choose the index whose R of I is minimum. Now why is that? So I will just try to prove it intuitively, and I think that proof should work because it is based on very strong arguments. So the thing is that if we place 1 at I, what happens is that for all values from I plus 1 to R of I, one segment gets reduced. One index, one possible index where these could have been placed gets reduced, right? So in a sense, what is happening is that if we are placing 1 at the ith index, then for all values from I plus 1 to R of I, one possible index where these could have been placed gets reduced, right? Because we could have placed any value from L of I to R of I. But if we are placing 1 here, then that means we are not placing any value from I plus 1 to this should be L of I plus 1, right? And L of I is equal to 1, so we can just write it as 2 to Ri. So if we are placing 1 at the ith index, then we are not placing any value from 2 to Ri. That means one possibility for every number from 2 to Ri gets reduced, right? So this is a loss, right? And what we want to do is we want to minimize the loss. We want to minimize the loss. And you can also think about it in this way, that if we have a valid permutation in which the number 1 is not placed in an index where R of I is minimum and L of I is equal to 1, then you can always exchange 1 from its actual location to the location where to this location where R of I is minimum. So you can basically always exchange. That is another strong argument, but I think this intuition is pretty much enough to understand that for all these values from 2 to Ri, we are incurring a loss, because they could have been very well placed at the ith index, but we are not placing them. So this is a loss, and we want to minimize the loss. That means we have to take the minimum value of R of I for all the values of I such that L of I is equal to 1. So this is the basic observation required to solve this problem. So now we will just talk about the actual solution. So solution. This is everything that we needed to solve the problem. So the solution in one word is basically sweep line. We will be using the sweep line technique. Now you will ask why the sweep line and how the sweep line is going to work, and if you aren't really familiar with what sweep line is, you can check out a tutorial that I have on it. I took a lecture on it a few days ago, so it would be found in the recent videos that I have uploaded on YouTube, so you are free to check that out. So basically we can apply sweep line, and in sweep line what we'll do is we will maintain all the active segments in the set, and for each I we will take the segment with minimum value of Ri and assign I to that segment's index. This is the basic solution. So what's happening here is basically what I'm doing is initially I put all the segments which start from 1 in my set, and out of all the segments I take the one with the minimum value of Ri, and then I assign that particular segment's index to the location of the number 1 in my permutation. Now what I'll do is I will delete all the segments which become inactive, that is the segments which end at 1, right? So now I have all the segments which are still active, but there are some segments which might start from 2, so I will add those segments into my set. So now this is how I will maintain all the active segments, right? So I'll just write it down, what are active segments. So active segments are segments which haven't been assigned yet. So these segments haven't been assigned yet, and they have started but not ended. So if you're not familiar with the sweep line technique, these things might not make sense to you, and if you are familiar, then you might think that I'm just repeating useless stuff. So in either case, I think this is pretty much enough to describe the solution. So we will just maintain all the active segments in our set, and we will just take that segment which has the minimum value of Ri and assign it as the location of the point I. Let's just have a look at the code we have completed with the solution. So the code is pretty simple. We maintain a set of pairs where the first number in the pair is the value R for the segment and the second number is the index for the segment, right? Okay, and now we basically have two vectors where adj of I denotes all the events which are starting at the point I, and ended of I denotes all the events which are ending at the point I, right? So L is going to be ceiling of I plus 1 upon bi plus 1, and R is going to be, if bi is equal to 0, it's going to be n, otherwise it's going to be I upon bi, as I have already discussed. So I will push back in adj of L R comma I, and I will push back in ended of R comma I. So this is basically useless. I could just have written an R here. So yeah, this is basic sweep line stuff, and then I go from 1 to n. I maintain my set. So for everything in adj of I insert it into my set. So now I have all the active segments, and I will just try to find out the segment with the minimum value of R and erase it and assign my answer. And then I will erase all the segments which are ending at the point x from my set. And finally I have my answer for all the numbers from 1 to n. I have found their location, and so I am outputting them, right? So yeah, if you are familiar with sweep line technique, you will be able to solve this problem really easily, and at least you will be able to understand the solution. But if you are not, I would just recommend to first learn what sweep line basically is, and then this would all start making sense to you, right? So yeah, this completes the solution to all problems and everything that I had in mind today. So thank you so much for watching, and I will see you in the next one.